lecture on regression. I defined what regression was, and I also... Regression is a very, very important topic in machine learning. It's, I would say, about 20% of all the papers produced in machine learning are on regression, maybe even more. And this lecture is not only related to regression, but it's related to other areas of machine learning. Okay? It tells you how to do well on data that you haven't seen. In other words, how to generalize. I'm going to talk about this technique. Okay, so we're looking at this model. We're going to assume this type of input-output relationship. X is the input, or I should say data, and Y is the output, or the label, target value. And this is the relationship between the input and output. And there is a very important factor, this epsilon, okay, which is like, you could consider it like noise. Okay, so let's say you have something and you try to measure it, and usually there is some noise, okay, in the instrument. Or this epsilon can be thought of as model error. Model error. Okay? So it's model error or just measurement noise. And when you have a situation like this, and you assume, in this example, if you assume that the noise is Gaussian, and you have to assume something else as well. You assume that it's IID. So if I put in x1 and I get y1 out, x2 out, and then I get y2 out, all of this, the noise that you add, the noise involved here, is sort of independent, but they're coming from the same distribution. And it's not related to x. Okay, it's not, this noise is independent of this. And one way of finding or estimating, so what we would like to do is, as for given x, some test data, we would like to find equivalent y. Okay? And the way we do this is maybe have a model. Our model is f, and our estimate of y, the true y, is f hat. Okay? And if we use this one criteria, minimum mean square, then it is same as assuming that fx is the conditional mean of that thing. Okay. So I went through this. So please have a look again. So now there is a little bit more in-depth analysis, similar to what was done in the previous page. Here you're given training data and training data and target value. You assume the noise is Gaussian. Okay? This is just an assumption. Or the model, the model error is Gaussian. So let's say I want to maximize my likelihood. Okay? What is my likelihood? So my likelihood is, if I assume that I know the noise power, sigma squared is noise power, by the way. This is an assumption, or variance. If if we know that, and we know the input, okay, and we have a model for f, we don't know what it is, and what's the probability of the output? And that would look like this. Why would it look like this? What assumptions have I made to make it look like this? First of all, I've assumed that all of the outputs are independent, right? So the joint probability has been decomposed into products of individual ones. And why is it Gaussian? How did I get Gaussian? It's a Gaussian with mean that plus variance that. Why is this distribution that? Because, what do we assume? Y equals this type of thing. Okay? What is the distribution of this? What's the distribution if this is Gaussian with zero mean? What is the distribution of this? Gaussian with variance sigma squared with mean what? Fx. Okay? So that's for individual ones, mean that, variance that. That's the distribution. Okay? And then we took the natural log of all this, and we're okay. So to do this, we get an ED. ED is that. So what do you do after this? What do you do this? So we have natural log of the likelihood, in terms of this. So what am I trying to do now? With this? I assume some model for my fx. And this is the model that I use. W transpose this. Why am I using this? What is this? Where do I get this? It's the linear basis model that I introduced in the very beginning of the class. Right? Remember this? This can model so this, depending on what phi is, it could be a mixture of Gaussians, it could be a polynomial estimate, it could be whatever you want. It could be a Fourier transform, depending on what phi is, how you define phi. So if you have phi defined, you define that before you start this. It's the problem of finding what the coefficient is, right? So you stick in this, into this thing, and that's your, so this is your hypothesis space. This is your hypothesis space. Okay, it's a whole bunch of these things. And you have the training data for that. Okay, training data for that. And what are we trying to do? What is unknown, first of all? What is unknown? These W's are unknown, right? We've defined what these P's are, okay? And so what do we have to do? We have the log, natural log of the likelihood in terms of, we know what n is. N is the number of data. We know what sigma is. This is the noise standard deviation. We know that. The only thing that we don't know is the W, right? So this whole thing is a function of W. So what do we do now? What's our next step? What is this? We have to what? Find a W which does what? That maximizes this. Right? And that will be our maximum likelihood estimate of W. Okay? So it really turns out finding the argument W that maximizes this is the same as the argument that minimizes because there's a minus sign, right? EE style. Okay, everyone understand what's going on right here? Now, what can you say about this? This result and the previous result, this is maximum likelihood, our criterion, 우리의 기준이 W를 찾을 때, 모르는 W를 찾을 때 maximum likelihood이었어. Maximum log likelihood. That was our criterion. What was our previous criteria? I didn't specify this. What was our previous criteria? 이거는 maximum likelihood을 해서 얻었습니다. 네? Previous page. I didn't talk about this. What was my criteria? What was my criteria? Was it log likelihood? No, it was minimum mean square. If I use this model to find my W, I didn't go through the math for that. Okay? I didn't go through the math. Would my answer be different or same? It would lead to the same thing. Okay? So that's all. So, different criteria, but maybe leading to the same thing. I want to show you another one. So that maximum likelihood was probabilistic approach. I want to show you an approach. It's called the residual square sum. Some people call it the residual square sum, or OLS, ordinary least squares. Ordinary least squares. Okay. And here, I will not use any probability. I will not use any probability. Okay. Maximum likelihood use probability. Minimum mean square use probability. Here, I'm not going to use probability. And I will show you how I'm going to do it. This is just to introduce mathematical formulation of this. Hey, here is my label for all the data, y1 through yn. And it's n by 1 dimensional vector. Okay, so n by 1 dimensional vector. And what I'm going to do, I'm going to estimate that as W transpose phi xi. So xi is equal to is W yi, like that. Or another way of, I'm assuming that fx is W transpose phi x. Okay? I'm going. This is my hypothesis space. I'm going to assume that I'm going to estimate yi as that. I'm not going to say equal, but I'm going to say it's an estimate. Okay? You understand what I'm saying? And I'm going to write this in a matrix form. So y1 is equal to W transpose phi x1. Okay? So this is how it's going to be. Look, that is that times that. Right over here. Okay. And I've assumed that the first one, phi. There's an I. I'm assuming that. So this is a vector actually. It is phi 0 x1, phi 1 x1, and so forth to phi x1 is a p. Okay, this is a vector. If you go to the very first slide of my lecture note, okay, that's how the phis work. This phi. Okay. And I'm going to assume that the first one is equal to 1. That is 1 right there. Or added 1. And W is this. W is W is W0 through W. Like that. So if I multiply this by this transpose that equals this summation of Wi phi x and 0 to p. That is my y. Right? That's what I had in my very beginning of the lecture. This is, and I just choose what the phis are. So in that matrix form, all that erased, it looks like this. That multiplied by that. And the second one is that multiplied by that. Okay? So that is in matrix form, and I'm going to call this this matrix, this bold, large phi x. Okay? Okay. Anyways. So, that's notation. So this is n by p plus 1. This is an n length vector, and that is a p plus 1 times 1 length vector. Okay? And I'm going to call this, that's phi. I'm going to call that big Y, bold Y, and I'm going to call this, here it is. Okay, so residual square sum, or least squares, what I'm going to do is I'm going to subtract the true label. This is the training label. This is going to be my estimate. My estimate is what? That multiplied by that. That's that. Okay? And I'm going to take the square of that. So I'm taking the error for each of the training data. And then I'm going to sum it up. Okay? So for each one of them, for each one of the data with data and label, I want to find the error between my prediction and my true thing, square error, and then I sum it up. That's what it is. And that's called residual square sum, RSS. So I put that, I substitute that in, and then this is what I get. Okay? This is a matrix form. What do you think I should do? What do I need to do after this? What is the problem? 뭘 하려고 그러는 거죠? 여기서. So I want to have a good prediction, right? So I found this residual square sum. So what? I want to, so one criterion might be, I want to minimize residual square sum. I want to find a W, because that's the only unknown. I want to find a W that minimizes the residual square sum. That might be one criteria that I might pursue. Okay? Find W that minimizes that. Okay? And what do you think the answer will be? Do you know? What W would minimize it? So you can think of it this way. Here is y, is a vector, okay? And so I'm multiplying this with that. So what is another way of thinking about this? So each one of this has to be very, very close, right? If this is minimized, then that's going to be minimized, and the total is going to be minimized. So how do this? How can you think about this? Can you think of it this way? In order to make this column, I'm going to take a linear sum of the columns of this. Linear sum dependent on these things to make that. Can you see that? So let me just say this thing one more in a different way. So here are a whole bunch of these columns. This is Px. See them as columns. And I have W0 to W1 and WP. So that is equal to some column times W0 plus, let's say that, first column. Second column times by W1 plus third column times by W2 and so forth. Can you see that? I'm taking linear sum of the columns to make this. Do you see it? The columns of these things take a linear sum to make that. Okay? So, in what space? This is, my next page will probably tell you. So this is lying in some n-dimensional space. N-dimensional, it's a point in the n-dimensional space. It's a point in the n-dimensional space. Okay? N-dimensional space. I'm trying to estimate that with the columns of B phi x. The columns of phi x, those columns in the big phi x, lie in this green area. Okay? These are one of the columns. That's another column. That's another column. And I'm going to take a linear sum of that to estimate that. You see? My phis, the columns lie here. Oh, here is my column, the first column. Here's my second column, and so forth. So, so this space, this green space, is the column space of phi x in the n-dimensional space. And here's my y. And what would be a good estimate? So I'm lying here to be as close to that as possible. So where should I be to be really close to that? Where? Right underneath. Rectangle, right over. So that's the point. What would that point? That's the point I want to be. To estimate that, right? And that point will tell you what? What W's to use. Okay? And if you go through that, so essentially what have I done right here in 10, I'll just explain this thing a little bit more, but I can go through this, and it turns out, so I want to minimize this residual square with respect to W, okay? So what I could do is take the derivative with respect to W, and W would look like that. The W would look like that. Ignore this for now. Ignore this for now. And I want to show you that I want to be right underneath. Okay? How do I be right underneath? I take Y. That's that point. That is what? The columns. So I take phi transpose. So I take the first one and sort of take this one and do a dot product. That will give me my W1. That one, and take the dot product of that. That will give me another W1, I guess. W2, and so forth. And doing that is this operation for all of them. So this is taking the inner dot product between that and that space. And this is somehow the normalizing, not the normalizing, but it's proportional. It will be proportional to that, and that will be the actual scale. Right here. Okay, so that is explained by this curve right here. So another way of saying that, how do I lie right below? I take the difference between my Y and my estimate. That's my arrow. My arrow and my space has to be perpendicular. Okay? And that leads to also that. That equation leads to that arrow. That's the arrow. This arrow is represented by that. And phi is that. Taking the inner dot product and making it equal to 0. Saying that equals 0. Okay, so that's arrow, inner dot product with a vector on this space and setting it equal to 0, so making it perpendicular. That's that equation. Okay? So what's the dimension of this? What's the dimension of this? N by P plus 1. Well, N by P plus 1. This is what? P plus 1 by N. So what is this? P plus 1 by P plus 1. Is that a small number or a big number? Usually training data is large. You have like maybe thousands, millions, lot. P, usually maybe, I don't know, 10, 20. So this is a small square matrix. Okay? And then you have to take an inverse of that. Okay? So this is computationally okay. Okay. Is this solution different from maximum likelihood? Go back to the page of maximum likelihood. where we use probability. I didn't go through the solution. It says minimize what? Maximum likelihood. Minimize what? ED. What is ED? It's RSS. It's the same as RSS. So maximum likelihood using probability led to some W. Using no probability led to some W. The same thing. Why do we get the same result? Why do we get the same result? 무엇 때문에 maximum likelihood랑 이 OLS 서로 다른 방법인 것 같은데 하나는 확률을 쓰고 하나는 확률을 하나도 안 쓰는. 무엇 때문에 무슨 가정 때문에 for what reason? Why are they the same? Can someone tell me? 저기 아는 것 같은데. Right. Because we chose that error in the previous example. We chose this. We chose the error to be Gaussian. If we had chosen something else, then the results would be different. Anyways, think about this. These are sort of deep insight. Anyways, another thing. What do you think? So this is a nice small matrix. You know, this is an inner dot product with the these, you know, the columns with the y. Seems all nice. Can you expect some problem if I have n training data, let's say a million, lot of training data. You think this is easy, or do you expect any problems with this? Do you expect problems with this? 제가 그러니까 I wouldn't have given you this question if there was no problem. There is a problem. And when when you're dealing with matrices, you are always worried about something. What are you worried about? Inverse. Inverse. Would I have a problem getting this inverse? When would I have a problem with inverse? When it's singular. Now think about it. Singular. Is it possible that I get singular? When do I get singular? 언제 singular하지? When does this become singular? When this is singular. Or what? One of these are singular. Now look at phi. Is it possible that you get singular? Look at it. Here is phi, my goodness. And I'm going to have a million of these, or whatever. Lots and lots of rows. And maybe P is 1, 2, 3. Obviously, it's very likely that one of these data are probably going to be similar. x1 and some xp. I have many, many combinations, but x1, maybe xl will be very similar. And what would happen? Then you would have rows that will be dependent. Do you understand what I'm saying? Oh, very difficult to get an inverse, because that's going to be almost many, many times singular. Okay, let's keep that in mind. So here it is, the limitation of this OLS. What if the columns are not linearly dependent? Or the columns are not dependent? Then we'll not have full rank, and that will be singular. Okay? And it will not be inverse. Or the rows, I should say. So OLS, very difficult. Minimizing the least squares or the residual squared variable. Not practical if you have lots of data. So what can you do in that situation? So we do this. Look at this formulation. We call this ridge regression. Okay. Ridge regression. Hey, I do this. What is this? What is this term? What was this term? The way I find my W is minimize this. What was this? RSS. Huh? And I do this also. While you add it, minimize that as well. So this is what I'm trying to find. So it's like the square of these W's for each W0, and so this will be, what is it? Summation of WI squares. Keep the W's small, not big. And lambda here is sort of a trade-off factor that I want to. So I want to, it turns out, if you have something that feed very close to singular, the W values that you get is going to be very, very big. Okay? And we can show you, I have examples, the textbook has examples, okay? But if you constrain that, okay, then you can, so you're doing both. So if you just do this, just do that, you get W values all over the place. But this will keep it in a range. So what is this? So what I'm trying in ridge regression, I am trading off ridge regression with this term. So if lambda is equal to 0, then I'm doing RSS. Okay? But ridge regression, I'm trading off. Hey, this is also very it's important, but make this small as well. Both of them. Okay? This is trying to make W very big. Okay? It's going to turn out W make very big. But this is saying, yeah, keep it small, but try to do this well. Okay? And lambda sort of trades off. And it depends on the application. And minimizing both of them is called, the solution is called the ridge regression solution.
Which regression?
Okay. And if you do that, what you get is this term right here. It's the same thing. You're taking the inner dot product with the columns of phi. Okay? And you used to have this, which has caused a problem. By introducing this lambda thing, I have lambda I. So what about this term? What about this term? What can you say about this? This is an I. I means it's a diagonal identity. So it's a lambda value. What can you say about this? This is never singular, right? You add something that may be close to singular to a full matrix, never diagonal. What happens to this? What is this? What can you say about this? This is full matrix, okay? So there's always, it's not never singular. Okay. Never singular. Let me just say that this, I want to show you why this W, maybe this, okay, this is the solution that we got. Why is that? When it's singular, what happens to the determinant? Very small, right? You take the inverse, what is it? Inverse is like, you take the inverse of the determinant, and then you have to do some different, to get the inverse. I don't know if you know this, I forget what, so let's say A, B, C, D. The inverse of that is 1 over the determinant over dA, I think minus B or C, something like that, right? What goes in right here? At the bottom, the inverse of the determinant. If you have a matrix that is very close to singular, this small number, so what is this number going to be? Huge. So what would you expect this W to be if it's close to singular? This W is going to be very, very big. Okay? This is just conceptually, I'm telling you that. If it's singular, it's going to be very, very big. Okay? So this thing right here is going to make W very, very big if it's close to singular. But what is this trying to do? Make W small. So they're acting in opposite ways. Okay? And this is your solution, never singular. And I should tell you, things like this, you have one thing, but you want something going in the opposite direction. This is called regularization. You're sort of regulating what, This is usually the loss function. This is the main thing that you want to do. And then you're sort of regulating what the solution is going to be. Controlling it. And what's the purpose of this regularizer? You are making the W what? Smaller. So it's a weight decay. And it also acts as a, what is this? Overfitting control. What is overfitting? What is overfitting? You are just overfitting is trying to do really well only on training data. I'm not worried about test. Okay? If you want to do 100 on the test, on the training data, forget about this. You just do that, even though W is big. Right? But what are you doing? You're controlling it with a lambda. If you have more lambda, then say, hey, pay a little bit less attention. If this goes up, we're putting more weight on this. Pay less attention to the training data. So you are controlling the overfit. Okay? And this is also parameter shrinkage, making it similar to that. Weight, the weights are making small. Okay? And I'll talk about sparsity a little bit later. It's another way of. So, we'll talk about this a little bit later. So, what can you say about this? What can you say about this? Through regularization, you can generalize better. Okay? Regularize it. Regularization. So you're not overfitting. Okay, there are many ways of doing regularization. And here is a general form of this. What is this first term? It's RSS. And here, well, you can sort of ignore the lambda s, but just to write it, to be safe. You can write it like that. And you're minimizing this with respect to W. Okay? Minimizing with respect to W. Go for this term. And you want to also maximize lambda as much as possible. And I'll talk about this a little bit later. Okay? This term. Writing it, you can write it like this, or you can formulate the problem like this. These mean the same thing. It's the same thing. Look what it says. This one is probably more understandable. Hey, minimize this, RSS, but do that. We looked at the case when the ridge regression was the case when Q it was 2. Q was 2, I remember. Okay? Each of the weights squared, sum of that. You wanted to bound it by, let's say, hey, don't make this, you can set this thing to any number. Hey, set this thing less than 10 or 5 or whatever. Do this, minimize RSS, subject to this. This problem can be formulated like that. It's the same thing. Okay? And I'll talk about this a little bit more about lambda. Do you know who has seen Lagrange multiplier? Lagrangian. I'm sure all of you have. Since you, who has not seen it? I look at some of your face and I see that some of you have it. This is first year math at KAIST. Who has not seen it? 자수하세요. Most of you are graduate students, so you should know how it is. Lambda, by the way, I haven't said it, it's called, what do you call it? Lagrange multiplier. Many else, some of us a little bit more. And this you have to understand this. If you don't understand this, you're going to have a tough time understanding support vector machine. Okay? Because it's all about constraint. You're optimizing. This is called, by the way, this terminology. What do you call this? This right here, RSS. Usually I could put an fx here. What is fx? It's called the objective function. Objective function. Okay. You are minimizing this criterion subject to this constraint. And we call this the constraint. Okay, and for q equals 2, we looked at this q equals 2 case. Now I want to show you what we're doing with this. What are we doing? This and that. This and that. What are we trading off? Okay, I've drawn the regularizer. Okay, by the way, this is the regularizer. Sorry. This is the regularizer with s equals 0. Or it could be anything. Okay? And it's for different values of q, the regularizer. Actually, I'm drawing this. This is q half. This is q equal 1. Okay. By the way, this axis was W1. This is W2. This is for two-dimensional case. Okay. Q equal 1. Q equals 2 leads to a circle. Q equals 4. This type of thing. What am I doing here? What am I drawing here? I've drawn two pictures now. One, the colored one, represents the regularizer. Okay? Regularizer. The first one is RSS. Okay? And I've drawn RSS with different as a contour plot. Okay? Why would the RSS look like this? Why would it be a circle? Why is it a circle? RSS is not a circle. It's a circle. Why is it a circle? Well, it's a quadratic term with the coefficients equal, okay, with W1 and W2. It's a square, okay? It's like that. That's just the loss function, the RSS. This is the regularizer, okay? And we're finding a solution. So do we want this thing to be big? What happens if this thing grows? Bigger contour. What does that mean? If you go out further out. 어떻게 돼요? 여기 뭘 뜻하고 여기 뭘 뜻하고 여기 뭐죠? What's happening? What happens as I go out? from the circle. RSS becomes bigger. It grows. Okay? And I have the regularizer. So I don't want this thing to grow too much, but it's going to hit my regularization. And the intersection would be what? My solution. Okay? Now, this is the case for ridge regression. Q equals 2. Okay? Q equals 2. This is the case for Q equal 1. The regularizer is like a diamond shape. 마름먹고. Okay? So you look at this and you say what? So obviously that the intersection is the solution that you'll be solving for. 여기서 뭐, which one is better? Which regulars, I should say? It's using same RSS here, but using different regularizer. Which is better? Which is what trade-off with it? Look at the intersection. You know, this point can be anywhere. This circle is lost function growing anywhere, right? And the intersection can happen anywhere around the circle, right? So that's that case, okay? What about here? Unless you have a very particular case, where's the intersection going to happen? Where's the intersection going to happen? 어디에서 교점이 일어나? 여기 꼭지점에. So what? Right? I mean, this circle is going to grow and then it's going to probably hit here rather than anywhere here. Unless you have a very particular case. It's going to hit at these. So is it better to have my intersection right here or anywhere? Which is better? Which is better? Depends? Depends on what? Depends on the problem. So give me a problem.
I don't know, at some point we might need to regularize it. At some point we might not.
We're regularizing both. This is both regularization. So you have a solution here. W1, it's going to be W star is going to be, let's say this is theta. That's going to be R. What is it? R. If it's what is it? R sine theta. R cosine theta. Something like that. Right? So you have some value here. Maybe that's a little bit wrong, but here what I'm going to have, it's either going to be something something and 0, or 0 and something something. Right? One of the W's is not needed. Okay? This, by the way, this type of Q less than 1 will give you where most of them are zeros and only few are non-zero, a sparse solution. Okay. Sparse solution. Sparse solution tends to generalize better. And it has many advantages. You've reduced the problem. You've reduced the computation. You've reduced the computation in getting the solution. Okay? Okay, so explained a little bit about ridge regression. Let's see. Okay, let me just look at this curve for this. Okay, let's look at this example for now. And by the way, it will also turn out, hey, this is all in, no probability. No probability in this one. But maybe you'll solve a problem in the homework. But look, we saw this was related to, in the probabilistic sense, this was RSS, same solution as what? Minimizing what? The likelihood. Okay? The likelihood as an exponential ED, if you remember. Okay, I'm going a little bit ahead. This is related to the likelihood. This is related to the exponential, to the prior. Okay? So I'm going to talk about this a little bit more. So you can approach a problem without using any probability. You can approach a problem based on probability, and it's going to lead to same solution. It means the same thing. Okay, and that is discussed here, but I'm going to go over it later on. So let's look at some examples. Okay, your goal: given X, predict T on the basis of, so you have X, given X, you want to find a corresponding value of Y based on training data with corresponding target value and target value. Okay? And let's assume, we don't only, this data was generated like this. So you take the X from here, 2 pi, side that, and add some noise. And that's how these T's were generated. Okay? XT pair was generated by this equation. Okay? And X here is between 0 and 1. This is how the data is generated. Okay? This is an example given in the book. Okay? So I'm just going over the book to explain some of the things. So I'm based on this. But I have no idea about this relationship. Okay? So I have no idea about this. Let's forget about this. So what I'm going to use, I'm going to use regression method to find a relationship. So one way is to find this RSS or the ED in the likelihood, okay, and define something like this. What is this? My prediction, given the input, and this prediction is going to be dependent on parameter W, okay? It's going to depend on W, and I want that to be close to Tn in the error squared sense. This is the error. This is my prediction. This is the true value. I subtracted. That's the error squared, and I want to do that for all training data. Okay? Okay. And let's say my y, I've decided to use this. Okay. What is this? I'm going to assume I'm going to make a particular, I want to make more detailed assumption. I'm going to assume it's that. So you give me an input, okay, and then I'm going to find these W's, of course, and then that's going to be my prediction. What is this? I'm doing what am I doing then? I'm doing this. What is this? A polynomial. What order? Nth order. Nth order polynomial fit on data. Okay? So when I substitute that in, obviously I want to get W that minimizes that. Okay? You understand the situation now? So, let's look at some of these graphs. I got about 7 minutes. And I want to make sure that you understand. M is the order. Okay? M is the order. And N is the number of data. The blue represents, okay, X is the X-axis, Y is the T-axis. And I have 10 training data. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 training data. Okay? And I'm going to, and the actual relationship between X and T is represented by this green thing. What is this? What was this green function? It was a sign, but we don't know that. Okay? Now I'm going to make my prediction with 0 degree. M equals 0. That's going to be what? It's going to be just a straight line. And that's represented by this red thing. Okay? That's M equals 0, M equals 1, M equals 3, and M equals 9. What do you notice? 무슨 트렌드를 볼 수 있을까요? As the order of your prediction, polynomial goes up, what do you have? Your prediction to the training data gets better, right? It gets better. It's going through the blue, closer, more. In fact, if it's M equals 9, it went through all of them. But what is happening? As this goes on, what's also happening?
Overfitting.
Huh?
Overfitting.
The W values becomes bigger. Okay? And it really goes crazy. Okay? And overfitting occurs. So let's look at this. This axis is the order of the polynomial. Y-axis is the error. Okay? On the training data, as the order goes up, what happens to the error? It goes to 0. Why do you go to 0? 왜 0으로 할까요? You have the number of parameters is the same as the number of data, and in that case, you should get all of them right. No? So the error is 0. Training. But on the test data, you generate new test data by what? We know what the relationship is. What? From 0 to 1, you take a value. You put it in sine 2 pi x. Then you add some noise. You could generate this test data, which was not involved in the training data. Look what happens. First it starts to the training. So this is the data that it hasn't seen. It falls, and then what happens? Shoot. No? Even the training error is in. So what do we call this? We call this overfitting. And let's look at the W's. We're going to use, when m equals 0, it's 0.19. M equals 1, like that. M equals 3. M equals 9. Look at that. The W's are crazy. No? Really huge. Okay. What is this graph right here? This, I have about 2 minutes. I have now more data, training data. Okay? And here I've used m equals 9. And you can see, is it crazy? So, if you have a lot of data, then you can have high complexity in your model. Okay? The previous situation, you had overfitting because you had too many parameters compared to what? Compared to the number of training data. Okay? It's always important. You have too many parameters. That's not the end. You have too many parameters compared to the training data. Okay? So here is the situation where I have lots of data, n15 for n equals 9. It was good. And this is for n equals 100. So it's a better fit to the green line. Okay? For n equals 9. So m equals 9, you may say m equals 9 is no good. By looking at that, this, and it's, it's very far from the green one, m equals no good, it's too complex. That's not right. It depends on how much training data you have. Okay? So this is a case. I was doing this. Ridge regression. And look. I have a very log lambda minus 18, log lambda more. And this is the case when m equals 9. Both cases m equals 9, and I only have 9 training data. Hey, look, what's happening? With a certain amount of this, for m equals 9, hey, it was following it fairly well. Huh? With certain regularization, even with a small number of data, I can do very well. Huh? But if I have too much regularization, I'm not following the true function, which is the green line. This is too much regularization. This is just about the right regularization for a small amount. And this is for different regularization, amounts of regularization. And you can see that here, this is training error, and this is test error. Why do you have this? Look at this. What's happening here? This, by the way, this is regularization. As I increase or the regularization, what's happening here? First of all, I had no regularization, okay? And so it's only loss function, so I had this overfitting, huge overfitting. Then with certain regularization, training and test data were very, very close. If I have too much regularization, what happens? It's not good for the training and not good for the test data. Okay, I'll just continue on. Any questions?